So far in our mechanics, all of the strings that we have considered have been light, inextensible strings. That is, when we apply a force to the string, it doesn't stretch. Now many strings will actually stretch when we apply a force to them. And such strings are called elastic strings. And in this video we are going to start our investigation into the properties of elastic strings. So, if we have an elastic string, then Hooke's law tells us that first of all the tension in the string will be zero if the string is not stretched, but the tension in the string will be proportional to the extension of the string, provided the elastic limit of the string has not been exceeded. So, if we've got our string just hanging naturally, and the string has a natural length of A, then if it's not stretched, it's just hanging naturally, there'll be no tension in the string. But if we then stretch the string a little bit further, so we've got an extension of length x, then Hooke's law is telling us that the tension in this string, which will be trying to convert the string's length back to its natural length, and this tension will be proportional to the extension. Now this isn't true for all stretches because you can overstretch a string, and we shall always assume that this elastic limit, the point of overstretching the string, has not been exceeded. So provided the elastic limit has not been exceeded, we've got t is proportional to x, or of course we can write that as an equation as t equals k times x. And k is called the string constant. Now if you're studying physics as well, you'll probably use the rule t equals k times x. In maths, we tend to use a slightly different rule, which says that the string constant is lambda over a, where lambda is the modulus of the string and is a materials constant, and a is the natural length of the string. So in mathematics, Hooke's law becomes t equals lambda x over a, where a is the natural length and lambda is the modulus of the string. And Hooke's law only applies provided the elastic limit of the string has not been exceeded. Now, the difference between a string and a string can be stretched, but it can't be compressed. On the other hand, a spring can either be stretched or compressed. So, if we've got a spring whose natural length is a, then we can extend the spring by distance x, and if we've extended the spring, we're going to have a tension in the spring, trying to take the spring back to its natural length. Now Hooke's law for an extended spring is exactly the same as Hooke's law for an extended elastic string. So the tension in a stretched spring is proportional to the extension, provided the elastic limit of the spring has not been exceeded, and we've got the equation t equals lambda x over a, provided the elastic limit of the spring has not been exceeded. If, on the other hand, the spring is compressed by distance x, then the spring will be thrusting outwards, trying to get back to its natural length. And Hooke's law again applies, so the thrust in a compressed spring is proportional to the amount of compression in the spring. And again, we've got the equation T equals lambda x over A. So let's have a look at some examples. So our first example, we have an elastic string of natural length 4 meters and modulus 80 newtons is stretched between 2 points A and B, which are on the same level with AB equals 4 meters. A particle is attached to the midpoint of the string and hangs in equilibrium with both portions, making an angle of 30 degrees with AB. Find the weight of the particle. So, as with most mechanics questions, we'll start by drawing a diagram. So we've got the points A and B are 4 meters apart on the same level. We've got our particle P attached to the midpoint of the string AB, and when it's hanging in equilibrium, the strings A to P and B to P make an angle of 30 degrees with the horizontal. Now the natural length of the whole string is 4 meters. So the natural length of half of the string is 2 meters. So the natural length of AP is 2 meters. Doing a little bit of trigonometry, we can see that the length of AP in this new situation is going to be given by 2 divided by AP equals cos 30. So therefore AP is 2 divided by cos 30, or approximately 2.3094. So the extension in the string AP is going to be 2 divided by cos 30, take away the natural length of 2, which is 0.3094. If we now add the forces acting on P, we've got its weight, we've got the tension in the string AP, and the tension in the string BP. They will be equal because both strings have got a natural length of A, and since they have both got the same length in the new position, the tensions will be the same in the same case. So we've got Hooke's law tells us that T1 and T2 are both going to be 80 times by 0.3094 divided by 2, which gives us a roughly 12.38 newtons. If we now resolve vertically, then we're going to get T1 sine 30 is going to be the vertical component of T1. T2 sine 30 will be the vertical component of T2. So upwards we've got T1 sine 30 plus T2 sine 30, and then we've got a W acting downwards. So overall we've got T1 sine 30 plus T2 sine 30 minus W must equal 0, since P is in equilibrium. We know that sine 30 is a half, so that gives me a half T1 plus a half T2 equals W. We also know that T1 is equal to T2, so a half T1 plus a half T2 is just equal to T2, so we've got T2, or T1 must equal W, which is 12, and therefore W must equal 12.38 newtons. For our second example, we have two springs, AB and BC, are joined end to end to a particle B on a horizontal table. The natural lengths of AB and BC are 1.6 meters and 1.4 meters respectively, and their moduli of elasticity are 20 newtons and 28 newtons respectively. We've got to find the tension in each spring and the equilibrium position if we know that the points A to C are fixed and 4 meters apart on the table. So let's start by putting in the natural lengths of the two springs, and by supposing that X is the extension of the spring AB. If the extension of AB is X, then we've got 1.6 plus X plus the extension of BC plus 1.4 must make up the whole of our 4 meters. So therefore, the extension of BC is going to be 1 minus X. And we can put that in on the diagram as well. Now, because we're working on a horizontal table, so we're looking at the diagram, if you like, from above, the only forces that we actually need to put onto the diagram are the tensions in the two strings. They won't follow the same rules, so we'll give them two different names. So we've got tension T in AB, and we've got tension S in BC. And if we apply Newton's second law to the right, then we've got S minus T must equal naught because the particle B is in equilibrium. And we can apply Hooke's law to the string BC to find an expression for S. So for the string BC, the modulus is 28 newtons, the natural length is 1.4 meters, and the extension in BC is 1 minus X. So we've got S is 28 times 1 minus X divided by 1.4. For the string AB, the modulus is 20 newtons, the natural length is 1.6 meters, and the extension is X. So we've got, by Hooke's law, T is going to be 20 times by X divided by 1.6. So the equation S minus T equals naught becomes 28 times 1 minus X divided by 1.4 minus 20 times X equals naught. 28 divided by 1.4 is 20. 20 divided by 1.6 is 12.5. So we've got 20 times 1 minus X. Take away 12.5x is 0. So that gives me 20. Take away 32.5x equals 0. So x is 20 divided by 32.5. Or if you like, 40 divided by 65. Or equally well, 8 divided by 13. Or as a decimal, we've got x is 0.615 meters. So that means the equilibrium position, we've got the distance AB is 2.215 meters. And in the equilibrium position, we've got T and S must be the same. T is probably the slightly easier one to work out. So T is 20 times by X, which was 0.615, divided by 1.6. So that gives me the tension in each spring is 7.69 newtons. This finishes our first video on elastic strings and springs. In the next video, we will look at the energy that is stored in a stretched string or spring.